Welcome back to the deep dive.
Great to be here.
Today we're diving into something really foundational. We've got these sources looking at Isaac Newton and his laws of motion.
Newton. Yeah, these laws are, well, they're basically the rules for how things move in the everyday world. Bedrock physics.
Exactly. So our mission today is to unpack them. What do they actually mean? Why were they such a big deal? And, how do they still affect how we see the world?
Right. We'll touch on Newton himself, obviously, then tackle each law one by one.
First, second, and third.
Yep. And then look at how they work together, where they apply, and maybe where they don't quite.
Okay, I'm genuinely excited. It feels fundamental, like looking under the hood of reality.
It kind of is. So where should we start? The man himself.
Let's do it. Isaac Newton. The sources paint a picture. English, 17th, early 18th century, 1643 to 1727. Mathematician, physicist.
Astronomer, author, and the list goes on. It's hard to overstate his impact. Truly one of the giants.
Yeah, the sources call him one of the most influential scientists ever. And it wasn't just motion and gravity, was it?
Not at all. His work in optics was revolutionary. Figuring out white light is made of all the colors.
And calculus. He basically invented calculus alongside Leibniz. That alone is huge.
Plus, the first practical reflecting telescope, he really did reshape how science was done.
His whole framework for motion and gravity, it just dominated for centuries, didn't it?
Absolutely. It was the way physics was understood until, well, Einstein came along in the early 20th century.
But even now, for most things we deal with day to day.
Oh, Newton's laws are still perfect. Perfectly adequate, incredibly useful.
And he had that famous quote, acknowledging those who came before him.
If I have seen further, it is by standing on the shoulders of giants. Shows a certain perspective.
Okay, so let's get to the laws themselves. Law number 1, the law of inertia. The source material puts it like this. An object at rest stays at rest, and an object in motion stays in motion with the same speed and direction, unless acted upon by an external force.
The core idea there is inertia. It's like an object's resistance to changing what it's doing.
If it's sitting still, it wants to stay sitting still.
And if it's moving, it wants to keep moving just like that same speed, same direction. Forever, really, if nothing interferes.
Which sounds simple, but apparently that was a major shift in thinking.
Oh, huge. Before Newton, the prevailing idea, sort of Aristotelian, was that things naturally wanted to stop. That you needed a constant push just to keep something moving.
But Newton says no, motion at a constant velocity is perfectly natural. It's change that requires a cause.
Exactly. That cause being an external force. And inertia is linked to mass.
More mass.
More inertia. Harder to get moving, harder to stop, harder to turn. Think pushing a shopping cart versus pushing a car.
Right. The car has way more inertia. Okay, the first part, at rest, stays at rest. That seems intuitive. My mug on the desk isn't going anywhere unless I push it.
Pretty straightforward, yeah.
But the in motion stays in motion part.
Yeah.
That feels less obvious because, well, things do stop.
They do in our world because we're surrounded by friction and air resistance. Those are the external forces the law talks about.
Ah, okay. So if I slide a book across the table, it stops because of friction, not because its natural tendency is to stop.
But precisely.
Yeah.
Take away friction and air resistance or minimize them, and you really see inertia in action.
Like the examples in the sources. Seat belts. That's a great one.
Yeah.
Car stops suddenly, your body wants to keep going forward, inertia. The seatbelt provides the external force to stop you.
Good one. Or think about a spinning top.
Keep spinning.
Due to inertia, it only slows down because of friction with the surface and the air whipping past it.
And sports on ice. Hockey pucks, curling stones. They just glide, don't they?
Because the ice has so little friction, inertia just takes over.
And the ultimate example, maybe? Space.
Right. Satellites orbiting. Once they're up to speed, they just keep going. No engines needed to maintain orbit because there's virtually no friction or air resistance up there. Inertia rules.
Okay, so law 1. Objects resist changes in motion. Inertia. That sets the stage for law 2. How do you actually make something change its motion?
Now we're talking about force, mass, and acceleration. Well, the source states it more formally. The acceleration of an object is directly proportional to the force applied and inversely proportional to its mass. But yeah, FMA is the equation.
This law basically quantifies it, right? Puts numbers on how forces change motion.
Exactly. Let's break down the terms. F is the net force, the overall push or pull, measured in newtons.
M is mass, how much stuff is in the object, measured in kilograms.
Yeah.
That's related to inertia.
And A is acceleration, the rate at which velocity changes. Speeding up, slowing down, changing direction. Measured in meters per second squared.
So the law connects these three. F, and the relationships pop right out. Double the force. Double the acceleration if the mass is the same. Push twice as hard, it speeds up twice as fast. Makes sense.
And if you double the mass?
Then you only get half the acceleration for the same force. Push a heavier object with the same effort, it accelerates less.
Right. It resists the change more strongly because it has more inertia.
The source also notes the direction is important. Acceleration happens in the direction of the net force.
Crucial point. Force is a vector, acceleration is a vector. They point the same way. And this isn't just for straight lines, it applies to rotation too.
Okay, applications. The sources mention rockets.
Classic example. The engine throws gas downwards with great force. That force, according to EFMA, causes the rocket, with its mass, to accelerate upwards.
More thrust, more force, more acceleration.
Yep. Or designing cars. You need an engine that produces enough force to accelerate the car's mass effectively. Performance versus efficiency.
Sports equipment too, like tennis rackets or golf clubs.
Absolutely. They're designed to help you apply a large force over a short time to the ball, maximizing its acceleration considering the ball's mass.
And airplanes. Balancing the engine thrust, force against the plane's weight, related to mass, and air resistance to get the acceleration needed for takeoff and flight.
EFMA is everywhere in engineering and physics.
Okay. Law 1, inertia. Law 2. EVA tells us how forces cause acceleration. But where do forces actually come from?
That brings us perfectly to Law 3, action and reaction.
The source puts it very simply. For every action, there is an equal and opposite reaction.
This is fundamental. It means forces never exist in isolation. They always occur in pairs.
So if I push on a wall,
the wall simultaneously pushes back on you. That's the pair. Your push on the wall is the action. The wall's push on you is the reaction.
And the key, according to the source, is that these forces are equal in strength.
Equal in magnitude, yes.
Opposite in direction.
Correct.
And they act on different objects. That seems really important.
It's the crucial part. Your push acts on the wall. The wall's push acts on you. Because they act on different things, they don't cancel each other out in terms of making one object move.
Right. If they acted on the same object, nothing would accelerate.
Exactly. And they happen at the same time, simultaneously. And they're the same type of force. If one's a gravitational pull, the other is too.
The examples really help here. Swimming.
You push the water backwards, that's the action. The water pushes you forwards, that's the reaction. That's what moves you.
Rockets again, pushing gas down and back.
That's the action. The gas pushing the rocket up and forward, that's the reaction. Works even in space because the rocket is pushing the gas, not the air.
Walking. I push backward on the floor.
Action. The floor pushes forward on you.
Reaction. That's what makes me move forward. Try it on sheer ice and...
Not enough friction for the ground to push back effectively. No reaction force, no forward motion, you just slip.
And a bouncing ball. Ball hits the ground, pushes down. Action.
Ground pushes back up on the ball. Reaction, making it bounce.
Wow. Okay, so those are the three laws. Inertia, EFMA, action-reaction. They seem simple individually, but together.
They form this incredibly powerful, interconnected system for explaining motion. Let's talk about how they tie together and their reach.
Yeah, the practical applications mentioned are just huge. Engineering, design.
Absolutely. Vehicle safety crumple zones, airbags, that's all about managing forces and changes in motion using these laws.
Building bridges, skyscrapers, designing planes, spacecraft, robots, machines.
Even down to sports gear. Designing a better running shoe or a faster bike frame, it all comes back to Newton.
And in science itself.
Foundational. Ballistics, how projectiles fly. Planetary motions, satellite orbits, understanding particle collisions, fluid dynamics, how muscles move bones. It all rests on this Newtonian framework.
But as amazing as they are, the sources are clear. They aren't the whole story, are they? They have limitations.
That's right. Modern physics has shown us where Newton's laws, well, break down or need modification.
Like things moving really, really fast.
Yep. Near the speed of light, you need Einstein's special relativity. Time and space themselves get warped in ways Newton never imagined.
And really, really small things. Atoms, electrons.
That's the realm of quantum mechanics. A whole different probabilistic set of rules governs the subatomic world. Newton's deterministic laws don't apply there.
And super strong gravity, like black holes.
Again, Einstein. General relativity describes gravity as the curvature of space-time, which is a much more accurate picture than Newton's force at a distance, especially in extreme conditions.
So they have these boundaries, but the sources stress that for almost everything we encounter.
From, bicycles to buildings to satellites, Newton's laws are not just good enough, they are essentially correct and incredibly useful. They are still the cornerstone of classical mechanics.
And it's cool how they fit together. The source material points out Law 1 is sort of contained within Law 2, isn't it?
It is, really. Law 2 is Fma. If the net force F is 0,
then acceleration A must be 0.
which means velocity doesn't change. That's exactly Law 1. Object at rest stays at rest. Object in motion stays in motion with constant velocity. So Law 1 is the special case of Law 2 when there's no net force.
And Law 2 gives the math for how forces do cause changes.
While Law 3 tells us where forces originate from interactions, always in those equal and opposite pairs, they really form a coherent package.
Taking a step back, it really is amazing. 3 statements formulated hundreds of years ago explaining so much of the physical world with such elegance and power.
They truly are elegant, and understanding them, even just grasped intuitively, gives you a much better handle on why the world works the way it does, why things move, why things start, why you feel pushed back in your seat when a car accelerates.
It definitely provides a framework.
Yeah, and it's the necessary foundation for understanding more advanced physics and engineering, too. You can't really get to relativity or quantum without first grasping Newton.
So here's something to chew on, thinking about those limitations. We have Newton's laws incredibly successful for our everyday world, right? Planets, cars, baseballs.
Right.
But then they just stop working accurately at very high speeds or tiny scales or near immense gravity. They're completely different rules apply. Relativity, quantum mechanics.
Yeah, the rules change.
So what does it tell us about reality itself? That the fundamental operating system of the universe seems to have different modes depending on the scale or the conditions you're looking at. How can these seemingly separate sets of rules govern the same universe? It really makes you wonder about the connections, the deeper theory, perhaps, that might unify them all.
That's the big question, isn't it? The quest for a theory of everything. It certainly leaves you thinking.
Well, thank you for joining us on this deep dive into Newton's laws. Hopefully it gives you a new appreciation for the physics happening all around you every moment.
Yeah, keep an eye out. You'll see inertia and action-reaction pairs everywhere now, I guarantee it.
We'll be back soon with another deep dive. Until then.